Hello dear students. Next method of numerical calculations for finding solutions of equations, regular falsi method. In the previous lecture, we have learned about the second method. Now we have to talk about the regular falsi method. So again we have the same assumption, that is we have to consider a smooth function, that is a function fx satisfying the equation fx equal to 0 is continuously differentiable a sufficient number of times. Also, assume that all the roots of the equation are simple, and we have to consider a sufficiently small interval a naught b naught containing the only root alpha of the equation fx is equal to 0, such that if a naught if b naught less than 0. Okay, we then proceed to generate the sequence xn of iterates as follows. We set x naught equal to a naught or b naught and x1 equal to a naught minus f a naught, b naught minus f naught a naught by f b naught minus f a naught. That is the slope formula, and compute fx1. This idea from the second method actually, right? So if you draw the diagram once again, this is the curve and this is the exact root alpha. This is your a naught, this is your b naught. So a naught and b naught, so these points are a naught f a naught, b naught f b naught. You look at that functional values at a naught and b naught are opposites, so this contains a root sufficiently small interval you have to consider. If a naught, if x naught, if x1 less than 0, first look at the diagram. One diagram you have to look at. Yeah, you are drawing these things, chord, and this is for n plus 1th iterate actually. So similarly, if you draw this one, you will get x1, right? So x1 is the approximation of the root. Again you will get second approximation similarly. So x1 is given by a naught minus f a naught, b naught minus a naught by f b naught minus f a naught, and compute fx1. Okay, this is the computation. This is your fx1. If fx1 is less than 0, look at that, fx1 is negative, so the root lies between x1 and b naught. But if fx1 is positive, the root lies between a naught and x1. So if a naught and x1 less than 0, we write a1 equal to a naught and b1 equal to x1. And if x1 b or b naught less than 0, we write a1 equal to x1 and b1 equal to b naught. So that in either case, if n1 if b1 less than 0 or a1 b1 contains the root alpha, right? That is the concept. We set again x2, same process, and repeat the above step and so on. So this is the concept of regular falsi method, or method of false position. If we generalize the concept, in general, having obtained the interval an bn containing alpha such that if an if bn less than 0 and xn equal to an or bn, we set this. This is the generalized one, and this is approximation n plus 1th approximation. So what is the geometrical interpretation? Geometrically, the ordinates fn and fbn are of opposite signs, and the chords joining the points an, fan, bn, fbn intersect the x-axis at the point xn plus 1. For the chord had equation, what is the equation of the chord? This is the equation of the chord, right? This is the straight line connecting two points. look at that, the chord joining A and Bn and Bn Fbn, right? So this is the equation of the chord. This is AB is the chord, and this chord intersect the x-axis at xn plus 1. So equation of x-axis y equal to 0. So if you replace y equal to 0, you will get x equal to this. So this will give you the xn plus 1, which is the approximation to the root, the point of intersection of the curve y equal to fx with the x-axis. So this is the beautiful and important geometrical applications, geometrical interpretation of the regular falsi method. And this is the iteration steps. Again, if you calculate the xn plus 1, what is the, if your fxn plus 1 ordinate is negative, then the root will lies between this and this, and so on. You can approximate. So look at that. There are several approximations starting from x1, fx1 joining by AB chord, then x3 again joining by BC, and so on, and it converges to the exact root on successive approximations, right? And what is the rate of convergence of the method? If the function fx in the equation fx is equal to 0 is convex in the interval x0 x1 that contains the root, then one of the points x0 or x1 is always fixed and the other point varies with k. If the point x0 is fixed, then the function fx is approximated by the straight line passing through the points x0 f0 and xk fk, k equal to 1 2 etc. So the error equation becomes, in this case you can calculate that as previous we have calculated in Newton Raphson and all that, epsilon k plus 1 equal to c epsilon naught epsilon k, where c is the f double prime xi by 2 f prime xi and epsilon naught is x naught minus xi is independent of k. This c star, actually the error equation is, this is the error equation, epsilon k plus 1 equal to c star epsilon k, and c star is the asymptotic error constant. And you see in this case, from this equation you see it is a linear rate of convergence. So regular falsi method has a linear rate of convergence. Okay, so this is the regular falsi method, and you can easily compare with this method with secant method. So only the Newton-Raphson method has a quadratic convergence, so it will converge very fast. We will solve problems later on in our class. Okay, so in the next lecture I will talk about the last method, that is the fixed point iteration method. Thank you all of you.